So we're going to go back and work on some non-make work examples for our for recursion. We're going to go over. We've already gone over factorial, but let's go ahead and just apply this to something similar, powers as a warm-up, and then we're going to go over greatest common divisor because that one's going to look a little bit different than anything else. We've already done factorial, right? Now, specifically, recursion is very nice in these mathematic examples because they are just naturally defined as being recursive. So, right, the definition for 0 factorial is 0 factorial is 1. N factorial is n times n minus 1 factorial. Right? So, let's go ahead and look at another math formula that we can define recursively. Go ahead and do long, public static long power, int base, int exp for exponent, not experience points. Okay, return 0 to quash it while I defined what the problem is. And here we are just simply going to calculate base raised to the power, right? So if I pass in, let's go ahead and do 2 as our power. That's pretty simple. If I pass in 2 and 5, that's going to calculate. So if I pass in 2 and 5, it's going to calculate 2 to the 5th power, which is 2 times 2 times 2 times 2 times 2 times, well, yeah, just 5 2's together. So 2 times 2, which is 4, 8, 16, 32. So would calculate 32. Right, and that's really, if you remember what exponentiation is, 2 to the 5th power, right? That's just us saying that we multiply. That's just a shorthand for writing out this, right? Much in the same way that that multiplication, right? If I did 2 times 5, much in the same way that this is just shorthand for us adding a bunch of stuff together. Make sense? Exponentiation is just shorthand for multiplying something together a bunch of times. So this will multiply it together 5 times. Okay, similarly, if we do 2 to the 6th, right, that is going to be equal to 2 times 2 times 2 times 2 times 2 times 2. One more of those. And so, the question is, how can we define this recursively? Well, first we need a base case. Can I multiply anything by 2 and kind of really have a really good idea of what it's going to be, right? And I kind of gave away the game there, but 2 to the 0th power, right? You might think, okay, 2 to the 1st power, I just returned 2. That's pretty easy. 4 to the 1st power, right? That would be 4. 8 to the 1st power, that would be 8. 7 to the 1st power, that would be 7, right? That's fairly straightforward, but even easier than that is just simply taking anything to the 0th power, because the answer is always going to be 1. So let's go ahead and say that. If, now we'll let that be our base case. If the exponent equals 0, return 1. Right? We'll return 1, because that's a very easy thing to do. Right? That's a very easy calculation to do. If exponent is 0, we'll return 1. So now we have to figure out a recursive definition. Right? And we kind of have our answer sitting right above that, which is, well, hold on a second. How can I calculate 2 to the 6? Well, 2 to the 6, right? That's 2 times 2 times 2 times 2 times 2, right? We're multiplying it by 2 one more time than we did for 2 to the 5th, which was 32, right? So actually, we could say that this is equal to 2 to the 5th times 2, right? 32 times 2. So the way we can define that, so right, and 2 to the 5th, that's equal to, well, 2 to the 5th is equal to 2 to the 4th times 2, right? So there's this kind of recursive definition for this power, right? It's we're multiplying it by the base one more time than the previous exponent did, right? So 2 to the 5th is 2 times 2 to the 4th. 2 to the 6th is 2 to the 5th times 2. Right? So x to the nth power is equal to 2. Well, not 2, right? But x times x times x times x dot 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 dot. It's equal to that n times, which is the same as saying, well, if we put together a bunch of these, if we put together a bunch of these guys over here, so if this is n x's, if there's n of these guys, if we put n minus 1 of them together, we can say this is x times, it's x to the, sorry, it's x minus 1. It's x times, sorry, it's x to the n minus 1 power. So x to the n is equal to x times x to the n minus 1 power. Right? That's what we've calculated over here. So else turn base times power int, sorry, power base, this should be the same, x minus 1. Right, and as we see, if we're given a positive exponent, this will make progress towards our base case because we'll keep subtracting from it. So go down here, power 5 to the 3rd power, 5 times 5 times 5, 125. So awesome, that works there. Of course, if we pass it a negative number, negative 1, sorry, yeah, negative 1, that really should be 1/5, right? But we get a stack overflow exception. Now, why do we get a stack overflow exception? Well, because negative 1 is not 0, so we'll return base times power base exponent minus 1. Which will pass a negative 2, which will pass a negative 3, which will pass a negative 4, getting it further and further away from our stopping condition. Totally not what we want to do there. So, if we want to actually make this kind of accurate, we'll need something else. We'll need to put in a separate recursive case here. Else if, it's a separate case. If our exponent is negative, exponent is less than 0, then what are we going to do in that case? Well, if it's less than 0, then we would like, well, how does that work? Well, if you remember from your mathematics that x to the n, where x is negative, x to the negative n is equal to x to the n, but under 1. 1 over x to the nth power. So we can still just, all we have to do here is just calculate x to the nth power. We'll still be doing that, but we can then put it under, we can then use it to, and divide 1 by it. So what we'll do is return, and we'll have to change the return type for this, return 1.0 divided by power base, same exponent value, but we're going to multiply it by negative 1 instead, right? So we'll take it, and let's see what we get. Incompatible types, required, long, right? So we turn this into a double. So what we're going to do here is we are going to pass in the base, and we're going to say, well, it's the same base, and it's the same next exponent, but we're going to multiply it by negative 1, which is going to flip the sign from of exponent to positive. So now if we run it, it should be 1 over 5, which is 0.2, 1/5, 1 over 5. So this should be 1/25. And a bit easier to calculate is if we do 10 to the negative 2, that should be 1/100th. Right, and this is guaranteed not to, and this is still guaranteed to work, because if it's less than 0, we just simply we simply flip it positive, and then since it's positive now, it will start subtracting 1 from it until it hits 0. So that in that way, we're assured that we're not going to hit this infinite loop, right? Because we flip it, we push it towards the case where it's going to be, where the recursion is going to work. So we're going to go ahead and do one more example, the greatest common denominator, in the next video.